Welcome, everyone. Thank you for joining us. This is a webinar on a new DLC report, Energy Savings of Network Lighting Control Systems. My name is Gabe Arnold. I'm the Technical Director with the DLC, and I'll be introducing the webinar and speakers. I'd like to begin with some webinar logistics. We have a lot of you on the webinar here today, so all attendees will remain on mute. We'd encourage you to ask your questions as we go, and you can do that by using the question feature of the webinar. Following the presentation, we will have a live question and answer period with our speakers where they will answer some of the questions that we have received. If we do not get to your question, we will follow up with you directly via email to get you an answer. So please do ask those questions. If you experience any technical issues as we go, please let us know via the question or chat feature of the webinar. Finally, this presentation and a recorded version of the webinar will be posted to the DLC website along with the report. So if you're not able to attend all today, or you have any colleagues that weren't able to attend, they'll be able to listen to this later. The project we are presenting to you today is part of a suite of resources the DLC has developed to support the market adoption of network lighting controls. These include a qualified products list of network lighting control systems that now has over 20 systems qualified. It includes a technology training curriculum to educate designers, specifiers, installers, and others on this new technology. It includes a savings calculation tool for utilities and others to use to estimate energy savings. It includes support for and collaboration with utility and non-utility efficiency programs and the development of new program offerings, rebates, and incentives for this technology, in addition to this report and project that we're sharing with you here today. The goal of resources is to support and accelerate the full-scale adoption of network lighting controls technology. The DLC works with the lighting industry, with utility and non-utility efficiency programs, the US DOE, Natural Resources Canada, and many others to break down market barriers, provide tools to enable scale, and bring people together to collaborate around our aligned objectives in support of energy-efficient lighting technologies. As you'll find out later in this webinar, this network lighting controls technology has potential to save a lot of energy. But that's not the whole story. It enables and unlocks tremendous value and new benefits to the industry, to building owners, occupants, and beyond. And our speakers will be talking more about that. We'd like to thank the sponsors and data contributors that made this work possible. We would not have been able to do this project without the help of all these organizations. The DLC received funding support from Efficiency Maine, Bonneville Power Administration, Natural Resources Canada, the Northwest Energy Efficiency Alliance, and Hydro-Quebec. That was really essential to us being able to do this project. In addition, as you'll learn later in the webinar, it was challenging to bring data in for this project. It was no small task, and so we are very grateful to the support of our data contributors that worked with us to bring in data. This includes AEP Ohio, RAB Lighting, NEDAP, Digital Lumens, Enlighted, and Berkeley Lab, Lawrence Berkeley National Lab. Thank you so much for your support. I'd like to introduce our speakers, and then I will hand things over to them. So first up, we'll have Levin Nock. Levin is a program manager with the DLC where he supports our work in both lighting controls and LED lighting. In this role, he manages the new DLC Network Lighting Control Qualified Products List, including development of the specifications, as well as overseeing the qualification process, working with manufacturers to have their systems qualified. On top of this busy role, he was the project manager on behalf of DLC on this project that we're sharing with you here today. Levin has a PhD in adaptive imaging from Duke, a BA in physics from Cornell, and a Sustainable Building Advisor certificate from Seattle Central Community College. Levin's very passionate about this work, and I think you'll enjoy the way he talks about it here today. Following Levin, we'll have Teddy Kish. Teddy works for Energy Solutions. Energy Solutions was the technical subcontractor to DLC on this project. At Energy Solutions, Teddy manages their emerging technology and product commercialization practice area. Much of his work focuses on how connected devices can generate insights that provide greater business value to utilities, end-use customers, and beyond to the supply chain. In his spare time, Teddy's an avid rock climber and spends much of his time thinking about global clean energy transition while dangling on the side of a cliff. Teddy, that doesn't sound very safe, but glad you're thinking about work while you're doing it. Teddy and all the team at Energy Solutions did some really great work on this project, and we're looking forward to sharing it with you here today. So with that, I will hand things over to Levin.
Thanks, Gabe. As an introduction to the report, I'll give some background about network lighting controls and a preview of our key findings. After that, Teddy Kish will present what we did in methods and what we found in results. Based on those results, I'll outline some recommendations that you can use in your work. At the end, Gabe will lead a session to address some of the questions that you submit through the webinar question box. Whoops, excuse me. Figuring out my clicks. There we go. So as you know, network lighting controls use multiple strategies to provide the right light at the right time without wasting energy on light that nobody needs. They use these 7 basic functions to do that, and some systems also support a wide variety of other control functions, such as personal control and demand response. All of the network lighting control products that are listed on the DLC qualified products list must be capable of all 7 functions listed here. So, all of the products that were included in this report are capable of all of these functions. The results that we found apply to any control systems that share these basic functions. For instance, Luminaire level lighting controls are one type of product that provides these 7 functions. Some of the products in this report used Luminaire level lighting controls with sensors and controls at every fixture. Other products used controls at every fixture for device addressability, plus a sensor for each room or zone, rather than inside every fixture. By the way, we'll see later on in the results, some of these functions like occupancy sensing were not necessarily activated in every building, even though the control systems were all capable of the functions. Why did we undertake this project? Well, now we get to the dinosaur. First, let me tell you a story about LED lights. A long, long time ago, when LEDs did not yet rule the earth or the lighting industry, the LED lighting industry was small, like the network lighting controls industry of today. Back in 2007, product specifications were limited and utility support was limited. Now LEDs have grown into a multi-billion-dollar industry. Today in North America, there are robust product specifications from DLC and Energy Star, plus over $200 million every year in rebates and incentives. Here at DLC, we believe that this support from specifications and incentives has helped the industry to grow larger. What was needed to set the stage for all this support from utilities for LED lights? First, information and demonstration reduced performance risk, so more building owners were willing to take the risk of trying these new products. Second, industry standards helped people compare products, in this case around photometrics and lifetime. After there was a critical mass of case studies and industry standards, then efficiency programs stepped in to offer financial incentives to reduce product first cost. Those financial incentives and rebates from utilities have played an important role in scaling up LED lights. A similar strategy could help scale up network lighting controls. But you might ask, why do network lighting controls deserve this support? Well, as we found in this report, network lighting controls have the potential to deliver energy savings above and beyond the savings from LED lights. In addition, they can deliver significant value beyond energy savings. New capabilities and features are unlocking new value for customers that is orders of magnitude greater than what has been provided by lighting in the past. Data provided by these network systems, both energy data and non-energy data, will unlock new value in terms of services such as the ones shown here, plus new business models to deliver these services. Here's the punchline. These three strategies were vitally important to accelerate the adoption of LED lights. In order to apply all three of them to network lighting controls, energy performance data is essential. That's why we undertook this research. This report will support all three of these strategies to help the network lighting industry grow and flourish. We had three main goals for this project. We wanted better estimates of energy savings from network lighting control systems controlling LED lights. Also, we wanted a database to collect energy performance data and data reporting guidelines for utilities and lighting control manufacturers. To meet these goals, we collected and analyzed data from 114 buildings with a total of over 1,200 building zones. And now, after that overview of network lighting controls, I'll introduce some highlights of what we found that Teddy will explore in a bit more detail. If you want a lot more detail, please read the full report. We found average savings in lighting energy from lighting controls of 47%. That was not counting any wattage reduction from an LED lighting retrofit. That was just for the controls. The portfolio of buildings that were included were simply selected because data was available. They are not necessarily a representative sample across different types of commercial buildings or across control products. They were simply buildings where we could get our hands on data from the network controls. Each individual building saved anywhere from 2 to 90% of the lighting energy. That's a large range, and Teddy will explore some factors that could account for some of that range. The main take-home point for efficiency programs and others is that at this point, you probably need to base your lighting controls program design or your customer savings estimates on a portfolio average of energy savings across all the participating buildings. It'll take some more research to develop better predictions of energy savings at the individual building level. Most energy reports from network lighting control products deliver insight for building owners and facility managers, such as an online dashboard telling the energy used in the last week or the last month. Those folks have data reporting needs and interests that are different from those of a utility. So for this report, most manufacturers found it very challenging to provide the data that we asked for that's important for utility incentives and rebates. Beyond that, a common data format for energy is crucial for interoperability, as lighting control systems are asked to share energy information with other products, such as energy dashboards, other lighting control systems, and other third-party applications for new services. We put some suggestions in Appendix A as a starting point for how manufacturers and utilities can move toward a commonly accepted framework for energy performance data reporting. Although manufacturers have an installed base of thousands of sites with network lighting controls, obtaining customer authorization for receipt of anonymized data was a major obstacle to the collection of data for this project. In order for utilities to run programs using energy performance data, they need an easy way to get the data from customers. Plus, in order for researchers to get more data to understand better the differences between buildings that perform well versus those that don't to develop best practices, customer authorization for anonymous data access will be essential. Beyond that, many of the new services and business models in network controls will depend on ways to share some data while keeping other data private. We put some suggestions in Appendix B as a starting point for how manufacturers and utilities can address this issue going forward. And now, here's Teddy Kish to dive into the details.
Thanks, Levin. wait 1 second so I can get control. Okay, so this is, as Gabe mentioned, a very large undertaking. And so we began the outreach and data collection process by contacting over 30 manufacturers, utilities, and national labs that were involved in NLC projects, asking them if they had completed projects with energy monitoring data, and if so, if they'd like to participate in this project. Roughly half of them had projects with data that was completed and were interested in supporting this effort. Our next step was obtaining data authorization with those interested organizations and going to their customers to receive an authorization for that anonymized monitoring data. And as Levin mentioned, the authorization ended up being a significant barrier, not particularly due to customer issues with it, but really due to that logistical challenge of tracking down the right person at each organization for an individual building. You can imagine when we're trying to scale up to hundreds of buildings, that doing that after the fact is quite challenging. And this is why one of the reasons why it's so important when we're thinking about streamlining this for data sharing and anonymized research, it's critical going forward to work with customers before the fact and have pre-existing authorization language. Once we had obtained the authorization to receive that anonymized energy reporting data, we worked with each contributor to securely transfer the data to us. We received project data from 6 contributors, and particularly manufacturers, as Levin mentioned, providing the data in this format was a major challenge because it was something that nobody had previously asked for in this level of granularity. So we definitely have a big shout out to all the data engineers from those 6 contributors who worked with us to support this data request. It was not an easy lift, and they did a tremendous job helping us out. And going forward, building on that, it's really important that the industry develops standardized reporting guidelines to streamline this process. So, as Levin mentioned, we collected data from 114 buildings across 7 building types, representing 5 manufacturers. And this energy monitoring data was collected at the zone and fixture level with an average of 60 days of monitoring duration post-installation after the network lighting controls were installed. And that equates to roughly 100 million rows of data that this whole system that we received from manufacturers. The chart on the left shows the number of buildings by each building type. So you can see that the majority of the buildings were in the office, retail, and manufacturing sectors, with some representation in 4 other categories. It's important to look at retail, where we had 1 NLC provider, and actually all of those NLC sites were 1 specific customer. And we'll get into some interesting findings with that specific customer later. The right-hand chart shows the number of buildings by NLC manufacturers. And as we discussed, since this was a voluntary data collection effort, some of the manufacturers are more represented than others. In fact, we have 3 manufacturers that represent about 90% of the data set. And so in future phases of this project, we hope to expand the sample size and get more broad representation across manufacturers for each building type. However, this is the largest data collection of actual monitoring data to date for the industry. So we think we're very proud of this accomplishment, and we're really excited about what we can continue to build on this. Overall, the project had broad geographic distribution across the US and Canada, with 26 US states being represented and 5 Canadian provinces. You can see that we had specific concentrations in the US state of Illinois and the Canadian province of Ontario. So how did we actually take this data, this 100 million rows of data, and from the contributors, and integrate them in a standardized format that we can analyze? One interesting thing was that because there aren't currently data reporting guidelines, we received this data from our 6 contributors in 18 different formats. which needed to be standardized so that we could work and analyze the data as one. So for each data format, our team developed customized scripts to import the fields in a standardized database. We imported both time series data, so for example, the power and dimming measurements that are recorded at a specific zone or fixture level for each time interval, as well as static attributes associated with that time series data. So let's say the building type, the space type, or the zip code that it was associated with. Once imported into the energy database, we are able to run custom queries to develop baselines for each building and identify energy savings. And an important note here is it's really not about the number of buildings that's an issue here. It's the number of different data formats and why streamlining that is so important. It's actually much easier to analyze 100 buildings in one data format than 10 buildings in 10 formats. So going forward, if we have data in a consistent format, we could easily imagine scaling this up to thousands of buildings over even longer periods of time than just 60 days, which with a relatively low incremental effort per building. So now I'd like to spend some time focusing on how we actually took that data and analyzed it to develop our baselines and resulting energy savings. So as Levin mentioned, the full details are in our report, so if you have any questions after this, feel free to dive in there. It's very well detailed. This graphic, as you can see, shows power of, which is shown in gray, of a sample zone within a building. And in this specific zone, you can see, for example, on Monday, people are coming in, the lighting power spikes up, it oscillates a little bit throughout the day, and then in the evening, probably around 5 or 6, lighting power goes down and basically shuts off for the entire evening. In the Tuesday morning, it starts up again. You can see that's fairly consistent throughout the week. There is some variation on Sunday where you don't see power actually going off at all between Saturday and Sunday, so something's going on there. So our method can be broken down into 3 steps. First, we use this measured power, so in gray, to establish when we think that zone is actually being occupied, using what we call an occupancy threshold. So we've defined it as 10% of the max measured power. So again, this is measured power here, and this is the 10% occupancy threshold. So whenever the measured power goes above that 10% occupancy, we deem that as occupied. Whenever it dips below it, say between Wednesday and Thursday nights, we count that as unoccupied. To calculate the energy savings, we identify the maximum rated power of the entire zone. So essentially what the entire zone, so the collection of fixtures within that zone, would be using without any controls installed. So if a luminaire is rated at 40 watts, we just, within a zone, we sum that 40 watt rated power across all the fixtures, and that becomes our maximum rated power within the zone. The energy savings then is the difference between that rated power within the zone and what we actually observe during occupied hours. And that's an important distinction. We are not claiming savings or calculating savings when we see that a building is deemed to be unoccupied. So there are multiple ways to baseline energy savings, but we chose this method for a few key reasons. First, it's unobtrusive. There's no pre-installation monitoring, and once installed, we're not asking building managers to disable controls, beginning to take baseline measurements. So it's unobtrusive, which we know is really important when you're trying to achieve scale. It's difficult to go to hundreds of buildings and actually get authorization to do this. It's logistically very, very challenging and likely improbable. Second, building on that, this approach is very scalable and reproducible. So once we're able to collect this data in a standardized format and integrate it in our database, we're able to apply this approach to hundreds of buildings on the order of weeks and the 1,200 zones, yeah, was on the order of weeks. And we foreseeably see this approach scaling up to thousands of buildings if the data format and authorization issues are resolved. Third, it's very project specific and highly granular. Each building savings estimate is based on the NLC monitoring data that we see here, and it's captured at the zone or fixture level. Moreover, with NLC systems, you can ostensibly collect this data from the same building multiple times over a multi-year period, or get multiple years worth of monitoring data, which would offer us detailed insights into how each building's performing over time. I think it's a tremendous benefit to the entire industry, manufacturers, owners, designers, specifiers, utilities, to really understand how network lighting controls are behaving, not just after the first week or 2 weeks or month, but over time for the next 1 year or 2 years, potentially, if we could get that data. We vetted this approach with a number of NLC experts, as well as those involved in utility evaluation and measurement, who endorsed our method. There are a couple of key caveats that I want to mention. That the savings, specifically the savings values represented here, are the percent of lighting energy savings during occupied hours relative, again, to that maximum rated power. So some key assumptions here are that the baseline assumes 100% operating hours or power during operating hours. And so that does not account for any pre-existing control strategies that may be occurring during operating hours. The second is that we do not count savings during non-occupied hours. So if network lighting controls were being used as a scheduling control, we don't pick that up because we're not assuming that the lights were on 24/7. So moving on to our findings, actually what we found. As Levin mentioned, the average savings were 47%, but I want to pause here to discuss what does that number mean exactly. And let's go through a theoretical example to clarify a little bit. So let's say we were starting off with a base case fixture that's 100 watts. So it could be a linear fluorescent, metal halide. Once we do an LED retrofit, the vast majority of these projects were with LEDs. So once we do an LED retrofit, and let's say it goes down to 60 watt, there's a 40% savings in this case from an LED retrofit. Now, if we layer on network lighting controls on top of that LED, the 47% only applies to the reduction going from LED without controls to LED with controls. So that's the 40% here. You do have a 68% cumulative savings that goes from the base case of that linear fluorescent or metal halide all the way down to LED retrofit with NLCs. However, for the purposes of the report, we are focusing only on that difference. That 47% represents the change from the LED retrofit without controls going to those with controls. So that's a summary of what we mean when we say exclude savings from Luminaire retrofits. Again, so we found that 47% value on an average, and this chart shows the number of buildings ranked from lowest to highest, and every color is a different building type, which we'll go into a little bit more detail. And you notice here that the savings really range widely. And this wide variation is likely due to the differences in both the control system settings and the site characteristics. So specific control strategies that may or may not be enabled at each site, such as high-end trim, occupancy controls, or even control settings. So if you have occupancy controls, for example, if you have a 5-minute occupancy timeout, it'll save a lot more energy than a 1-hour occupancy timeout. Other important things are site characteristics. Occupancy patterns, every building is different, and so occupancy patterns naturally vary across buildings, as well as opportunities to leverage things like daylighting to reduce energy consumption. through the network lighting control system. For example, in the Energy Solutions has a network lighting control system in our building, and we've seen over 80% reductions in use relative to a LED luminaire without controls. So when you see these 80 to 90%, that's likely what's happening is that they're using aggressive high-end trim and occupancy controls. And so I'd like to get into an example of what actually a high savings building looks like and what those site characteristics may include. We do see a very wide range of savings across buildings, and then while we're not, we had limited data fields that we were able to collect, and so while we're not able 100% to attribute savings to each specific control strategy, by looking at time series data like this, we can start to get clues about and make generalizations and hypotheses about what's driving the savings. So this graphic you see here shows, again, the power over time. This time it's specific to a warehouse. And you can see that the power draw is consistently far below the maximum rated wattage. And so because we don't see any major spikes that go all the way up to full output, it's likely that high-end trim in this specific zone is cutting down the maximum light output and possibly combined with very aggressive occupancy controls that quickly shut off the lights when not in use. You can see the occupancy controls are probably used pretty aggressively because you see a spike here on one day, but throughout the rest of the time, the power is much, much lower. Other factors that may include or attribute that savings would be daylight harvesting, or that, again, has high swings in occupancy, and the use of scheduling controls. Now, not every building, as we saw in that sample, not every building is achieving high savings. Some ones are achieving low savings. And so we wanted to elaborate a little bit more about what might be the causes for those. In this case, you can see that this building, this is a manufacturing facility, you can see that this facility is essentially, looks like it's operating as a scheduling control entirely. For example, between Tuesday and Wednesday, the lights are off. Wednesday, the lighting power jumps up to 100% of rated output. It's flat during the day, and then it drops down to 100% off. So it looks like there's really just scheduling going on, and the lack of any variation at the top suggests that there's not really any occupancy controls either being enabled, or that the building doesn't have occupancy shifts that would allow occupancy controls to take advantage of that. It's one of those. And so this was fairly common in facilities with low savings. And so given our limited data, we were not entirely sure what is the causal mechanism, but it's an important aspect when we think about how we could improve savings at sites. You know, we saw an average of 47%, and we have a lot of high savers. You know, what can we do with sites that have low savings to move them up towards the higher performing sites where possible? And that would increase the overall potential energy savings that we'd see as a portfolio. This chart shows the range of energy savings that we observed across all sites, separated out by building type. Each small circle represents the savings from a single site, with small black lines representing the maximum and the minimum for that building type, with the thicker dark green lines and the average values are represented in the middle there. So for example, in office, the average savings we found was 63%, in manufacturing 82%. As you can see, even with building type, there's a very wide range of savings values here, and we don't see a strong correlation between building type and savings value. The range is quite large within each. The lone exception is for warehouse, where warehouses are pretty closely clustered around 80% savings, and they also have the largest savings opportunity. And so while our sample size was fairly small, this generally agrees with previous analyses that suggest that warehouses are among the best savings opportunities for NLCs. Offices and manufacturing had the widest variation in savings, ranging from almost 0 to up to 90%. And while these, especially offices, while they're quite spread out, you can see that there's strong clustering within our sample around the 80% range. And this is likely due to the fact that these sites have ideal site characteristics for NLCs, and they are likely employing many of the tactics that we discussed earlier that can achieve those higher savings, such as aggressive occupancy and high-end trim throughout the building where it makes the most sense. Our retail results provide a really important insight into just the natural variation across NLCs. As I mentioned, all 29 of these buildings are from a single retail customer who likely implements fairly similar operating hours, stocking practices, and building operation in general. And so you do see the clustering around 45% or so, but there is still a variation, and that's, I think, just comes from each building being naturally at a different site and having different characteristics. Across all buildings in this study, we found that operating hours in the buildings with network lighting control systems were all above average when we compared to typical prescribed estimates of operating hours that some efficiency programs use to set baselines. This chart shows each building type horizontally, and then on the bottom we have the annual operating hours going from 0 to 8760. And you can see across the 4 regulatory environments that we surveyed, the operating hours that we observed in our buildings, which is again, we define operating hours as when a building is occupied or it exceeds that 10% threshold. The operating hours were significantly higher than what was a deemed value here. And I think that's an important takeaway, because in virtually all cases, we're seeing significantly longer occupied hours than what utility programs are allowed to claim. And this may be due to the fact that buildings that are good candidates for network lighting controls may just have longer runtime hours than other buildings. We're not entirely sure what the causal mechanism was, but we do see that this is a fairly uniform result. And so we think that this is important to study further with a larger sample size. And if it confirms these initial findings, we think that utility programs could potentially be able to claim these longer operating hours for their network lighting controls, which would then potentially provide larger customer incentives and greater savings claims. And with that, I'll hand it back over to Levin to summarize the recommendations.
Thanks, Teddy. Whether you're an energy efficiency program manager, a building owner, or anybody in the supply chain who's talking with building owners, you're more likely to see positive results from lighting controls if you can talk about a portfolio of buildings. And you can develop best practices to apply across all the buildings in that portfolio. For instance, you can make sure that all the systems are properly commissioned, so high-end trim, occupancy sensing, and daylight harvesting are all enabled where feasible. As you may recall, buildings on the right-hand side of this chart with the least savings tend to use lighting controls as a simple time clock, as Teddy just mentioned, without any other control functions. Now granted, if the lights used to be on 24/7, then that is substantial savings, just adding a time clock. But there's a lot of savings available beyond that in most buildings. So if there were no buildings like that were just using a time clock, then the portfolio average savings would be higher than 47%. Our next recommendation is about Appendix A. It provides a draft for a common data reporting format. This is a place to start that could be developed later, eventually, into a standard. Both lighting control manufacturers and for energy efficiency programs please take a look at Appendix A as a way to help the industry move toward a commonly accepted framework for energy performance data reporting. If utilities can start using this format in their programs, and manufacturers can start supporting it in their products, that will make incentives and rebates flow more smoothly. Besides that, it will support future research that can lead to higher savings and higher rebates. Also, a shared format across multiple products could meet the needs of building operators for interoperable systems and systems that support future third-party applications. This slide shows a snapshot of part of the table that's in Appendix A. There's a data element on the left with a definition, a data type, the unit of measure, etc. So please check out the report for that full table. One of the biggest headaches in this work for almost everybody involved was chasing down customer authorization to use each customer's anonymized data for research. When somebody downloads a phone app, they accept a data licensing agreement. You can imagine something similar for data sharing when a customer signs up to get a rebate or incentive. Data authorization is a critically important step, and it needs to be done when the system first goes in and gets an efficiency incentive. In addition, manufacturers, distributors, contractors, and basically anybody who engages with customers could clarify who exactly is responsible to provide energy data for utility reporting. In order for utilities to run programs using energy performance data, they need an easy way to get the data from customers. Plus, in order for researchers to get more data, to understand better the differences between buildings that perform well and that don't, customer authorization for anonymous data access is essential. We put some suggestions in Appendix B as a starting point for how to address these issues going forward. The topic has important implications for data security and privacy, and we hope that you'll at least give it some thought. Here's a summary of our main recommendations. Adopt a building portfolio approach, adopt a standardized format for data, and implement data sharing agreements with building owners. So where do we go from here? This report has 2 months of solid energy savings data based on modern digital networked lighting controls, controlling LED lights in over 1,200 zones across 114 buildings. It also has a foundation for a common data format to exchange energy performance data for lighting rebates, incentives, and new business models. These are unprecedented and powerful tools that can advance the lighting controls industry. What to do with these tools is up to you. Manufacturers can start reporting energy performance data in a consistent format. Utilities can start requiring energy performance data in a consistent format. Both groups can modify and elaborate this foundation as needed to move toward genuine industry standards. Anyone who deals with building owners, from designers and specifiers to contractors and lighting representatives, can quote this report as a third-party reference for what to expect in energy savings, and as a resource to navigate questions about sharing data. You can download the report at designlights.org. There's a big button right now on the home page that says Download Report. And if you're listening to a recording of this webinar later and that button has disappeared, as it will eventually, then you can use the full link at the bottom of this slide. And thank you very much for attending. And now I'll turn it over to Gabe to lead the question and answers.
All right, thank you, Levin and Teddy. We got some good questions here, so we're going to go through as many as we can with the 13 minutes we have left. Anything that we're not able to answer, again, we know who asked the question. We've got your email that you registered with, and we'll be sure to follow up with you and get you an answer. So first question, I think this one's maybe a good one for Teddy. What methodology was used to isolate the energy savings associated with the network lighting controls versus the LED fixture or lamp?
Yeah, so in most cases when we were working with the manufacturer, they would have the rated wattage of the LED that was going in, and so we used that as a maximum. And so that was enabled us to isolate the retrofit. And in some cases there were some cases where we did not have that, and then we worked with the manufacturer to identify what that rated wattage would have been. So essentially we were able to eliminate the pre-LED value from our system, and then our calculations are only based on the LED fixture assumed wattage.
Thank you. Okay, another question. I think this may have been on the slides, but maybe you could elaborate a little bit. So what is the accuracy of the data, since the data was collected from many different sources and probably different types?
That's a great question, and as we all know, there's many different ways to do energy monitoring. There's different methods that you're actually recording the energy. There's using true power, there's correlated power, and apparent power. There's different measurements for power, and because this was a first cut and it was voluntary data collection, what we did was we recorded what type of power measurements each provider was using, and the sampling rate, so how quickly they were creating those power measurements, and also the reporting rate of how often they were rolling those sampled measurements up. So we recorded that, but because again it was a voluntary data collection, we weren't able to be, let's say, really picky. We didn't require that everyone had true power, but we did measure and identify every source that came in, what type of power measurement it was using. Going forward, as more people adopt true power or more rigorous measurements of power, we would analyze that too and potentially consider that as part of our analysis going forward.
Okay, thank you. Probably another one for you, Teddy. I think they were asking this as you were talking about collecting the data. Why would one manufacturer have multiple data formats?
The multiple data formats came primarily from our utility, where they had many different projects and a range of data formats that they had. So it was when the utility had a program and there were many different contributors and manufacturers that had participated, and so when they provided that data, it was over their range of manufacturers. The individual manufacturers all had different formats, but the major challenge was when the major variation in data formats was from a utility.
Okay.
I would add to that some manufacturers did have different parts of the data puzzle in different databases. For instance, the energy savings data might not be in the same database as the space commissioning data that would tell what a particular space type was. So there were cases where each manufacturer might have to go to multiple databases of their own internal database and combine them.
Okay. So question, is rated power a good baseline if normal behavior is to turn off lights as you leave a room or building?
I think that's a good question. One thing that we would like to do going forward is get a better sense of whether that's the case. Again, because we didn't have access to that. That's something that in the future, what would be interesting to do is when programs are implementing network lighting controls projects, if they're doing some data collection, on a small number of those projects, doing some baselining, let's say for their evaluation purposes, we would start to get a better sense of whether or not that's the case, and if we would need to make any modifications to these assumptions. So we've addressed that in the report somewhat, and it's I think an important consideration that we would like to do in future iterations for sure.
Okay. More questions about the baseline. Do you think it would be worthwhile doing pre and post metering to test the accuracy of your simple baseline method or your inferred baseline method?
Yes, I think that's something that we definitely recommended as part of that, is looking at, we had a couple sites where we did have some, we had access to actual baselining and actual third-party reviews. So we had their data, and so we were able to compare our method to another's, and that's detailed in the report. And so that we would encourage that happen over time, and so I think that would allow us to refine this method over time. So it's definitely something that should be considered going forward.
Here's a comment. I'm not sure there's a question in it or not, but it's a comment that your occupied threshold, so this is about the baseline again, looks to be greater than 10% of the max measured power.
This is Eric Rubin. Can you hear me right now? Is my volume on? This is Eric Rubin from Energy Solutions. I saw this comment come in during the webinar, and I actually went looking to find the source graphic, and it's true. That's actually a mistake. It uses a higher fraction. We did a sensitivity analysis where we were trying out different occupied thresholds to see to what extent it affected the results. The answer is very little, at less than 5% change in the results, depending on if we use a wide range of occupied thresholds, and that graphic is actually from a higher percentage. So that's why that is. But we did use 10% for the results presented in the report.
Okay. All right, here's another question where I'll take a shot at the answer. It's a two-part question. How would DLC recommend that incentives be framed? Prescriptive based on power managed? Does it make a difference? Does the size and complexity of the NLC vary for larger applications? And are you aware of any incentives currently for network lighting controls? So yes, in fact, there are about 24 utilities that are using the DLC network lighting control QPL to provide incentives, and there are about a dozen that have developed some new, I think, very innovative ways of supporting this technology, actually some targeted incentives around that. You can find some of that information on our website. If you go to the members section and look at the program summary, you can see what utilities are offering incentives at this point. In addition to that, the DLC is about to launch a new project where we'll be working with the utilities that have moved forward around this technology to identify what some of the best practices are, how things are working with some of these new approaches, and taking that information and making it available to other utilities across the country to try and support their efforts to develop new incentives around this technology. So if you are a DLC member, there will be a lot more information coming soon about this. In the meantime, you can check out our website and also follow up with us directly, and we can point you to some of those examples of the utilities that are currently providing some specialized incentives for this technology. Okay, there's a question about the average hours slide. So they wanted us to explain it again. It looked to them like the inferred occupancy hours that energy efficiency programs use look longer than the observations. Levin, do you still have control?
Yes, I can go back to that slide. It will take me a minute. There we go. Yeah, so if you look at the bottom axis, it starts from 0 hours over on the left and goes up to 8760 hours for 1 year that's on the right. And so then if you look at the different building types along the vertical axis, for instance, for assembly, you can see the TRM benchmark. For assembly, there was only a reference for California Deer and for New York. But for instance, the California Deer reference says that assembly buildings are occupied around 1,800 annual operating hours. Let me see if I can use my mouse. There we go. That's around 1,800 versus what we found for the buildings, the assembly buildings in this study. We found they were up around 4,500 hours. So when we were saying that the operating hours we found were longer than expected, we're saying that this 4,500 is larger than this 1,800. And that was surprisingly consistent across building types. That in fact, manufacturing was the only one where we overlapped at all with this estimate from Illinois. But otherwise, all of our estimates were higher.
Thanks, Levin. One more question in our last minute. I think it's an important one, especially for the efficiency programs. Maybe we could try and give a quick answer on it. Has there been any vetting or input from the evaluation community to mitigate EM&V measurement and verification risk to utilities of using portfolio average savings, then seeing specific individual projects sampled for development of a realization rate?
I think we originally, so one of the people that we reviewed our approach with was an evaluator, but I think it's an important evaluation question as more and more programs adopt controls, because as we saw with just that one retail customer, there's going to be always natural variation. This isn't just as simple as installing LED luminaires, which have a fairly consistent operation. The savings come from control. And so the portfolio, it's likely that we'd need to use a portfolio, or that'd be one of the options. And that evaluation, we recommend that the continued discussion with evaluators for sure. So it's an important aspect.
Yeah, maybe while you're building the program, you can work alongside your evaluators to make sure that this is understood and come to an agreement about how to best evaluate it at the back end, so they're not getting dinged when we have this understanding up front. So that concludes the webinar. Thank you so much for joining us. The webinar will be posted to the website. Any of the questions that weren't answered, we will follow up with you individually, and we hope you enjoy the rest of your day. Thank you.